Hello, everyone. My name is Jiamin. I'm currently a Marie Curie Fellow affiliated with the Max Planck Institute for Extraterrestrial Physics, as well as the University of Florida. I'm very glad to give this talk to discuss the challenges in probing parity violation with large-scale structure and to explore the next steps forward in this exciting area. Here is an outline of my talk. I will begin by reviewing the measurements we conducted with the bot survey, including the measurement itself and our approach to quantifying detection significance. Then I will discuss the challenges involved in this measurement and the current status of our findings. Finally, I will outline the future directions and next steps we plan to take in this area. So let's get started. Before discussing asymmetries in the universe, let's first look at some examples of symmetries in nature. On the left, you can see a slice through a map of our universe where each point represents one galaxy. The galaxies are color-coded by their redshift, and this map is from the Sloan Digital Sky Survey. So this map illustrates the cosmological principle, which states that our universe is homogeneous and isotropic on large scales. In other words, there is translational and rotational symmetries on cosmological scales. A parity transformation then involves flipping the spatial coordinates, going from x to minus x, y to minus y, and z to minus z. While parity violation was already detected in the 1950s at atomic scales through weak interaction, we have not yet confirmed parity symmetry on cosmological scales. And importantly, there is also no fundamental reason to assume that the symmetry must hold on large scale by default. So if parity is indeed violated, it could imply presence of new physics, either originating in the early universe or at later time. There are various ways to probe parity symmetry, and in the first part of my talk, I will focus on using galaxy four-point functions. To illustrate this concept, let's use a simple example with this cartoon. And here we have a galaxy tetrahedron, where each vertex here represents one galaxy. We arrange the relative separation among the galaxies to be the R1, R2, and R3, such that R1 is smaller than 2 and then 3. So when viewing from the above, the tetrahedron has a clockwise orientation, which we can use to assign an effective handedness to it. Now, if we create a mirror image of the tetrahedron and compare it to the original one, we observe that the handedness at each vertex gets flipped. And if we imagine repeating this process with simpler shapes, such as a line or a triangle, we can always recover the original image through a rotation. However, for a tetrahedron, this is not possible because the transformed tetrahedron will not overlap with the original one. And this demonstrates two important points. So first, in 2D, a parity transformation is equivalent to a rotation. While in 3D, a parity transformation involves a mirror reflection and combined with a rotation. And in practice, we use the isotropic basis function probed by my collaborator, Robert Kahn and Sakris Lapin. So on the left of this equation, this is an ensemble average of products of the density field, which is also the definition of the endpoint function. And the idea behind this approach is to decompose the function into a radial dependent term and an angular dependent term. So this angular dependent term is called the isotropic basis functions. So this basis function can be further written as products of spherical harmonics weighted by a CLM coefficient. And this coefficient itself composes of products of the Wigner-3J symbols. And this basis has many nice properties and allow us to accelerate the algorithm for endpoint estimator. Taking this four-point function again as one example, Traditionally, when we calculate the 4-point function, it requires sitting at a primary galaxy and search for its three neighboring galaxies simultaneously. And this results in a high computational complexity. However, using this function, we can reduce the complexity significantly. Instead of evaluating triplets for each primary galaxy, we only need to count galaxy pair. And for each pair, we compute the associated coefficient accumulated onto the primary galaxy and repeat this process for all the galaxies in the simulation or in the survey. So as a result, the complexity scales similarly to that of a 2-point function rather than a 4-point function. Another powerful feature of this basis function is its sensitivity to parity transformation. When we flip the spatial coordinate for R1, R2, and R3 to minus R1 to 3, an additional phase emerges. And specifically, if the sum of the three angular momentum for these L1 to 3 is odd number, then this function will flip its sign. And this property allows us to detect parity transformation effectively with this basis. Moreover, to further illustrate this point, we can rewrite the harmonic representation of this basis function in Cartesian coordinate. For instance, the term P111 denotes the L1, L2, L3 all equal 1. And similarly, we can have configurations like P122 and 133, and which with each of these index indicating a different angular momentum component. In principle, these indices can extend to arbitrarily high values. And in all these cases, we see that a scalar product structure enters in the basis function. And this feature indicates that the basis function inherently encodes three-dimensional coordinate information. And this is essential in capturing the parity transformation. So to quantify the detection significance, we compute the chi-square statistic. And this calculation involves three key ingredients: the data, a theoretical model, and a covariance matrix. So the overall idea is that we will measure the chi-square for both the data and also for the simulation that has no parity violation. And they are also consistent with GR. And then if the chi-square value from the data is statistically distinct from that simulation that has no parity violation, they could serve as an indication of new physics and possibly pointing to the presence of parity violation as well. So here for the data, we use the BOT survey, which consists of two subsamples, the CMAS and also the low C. The CMAS sample covering a higher redshift range and is larger, whereas the low C sample covers at a low redshift and has a smaller in its size. In the left panel, it shows the number density as a function of the redshift for these two samples. And for each of these samples, we measure the 4-point function correlation coefficient characterized by 3 angular channels and also 3 radial bins. And as an example, we consider the case where the 3 L's for the L1, L2, L3, they all equal 1. And in this right plot, the red and the blue dots represent measurements from the northern and the southern galactic caps, respectively. And in this test, we performed a model-independent search with the null hypothesis, which means that we set the theory term to be 0. And regarding the covariance matrix, we tested different approaches, including a pure mark-based covariance, an analytic covariance template derived and also tested in this paper, and a hybrid covariance. And finally, as mentioned earlier, we compare the chi-square values of the measured data to the empirical distribution obtained from the simulation that does not include parity violating mechanisms. And this comparison allows us to assess whether the observed data significantly deviates from what would be expected under models with no parity violation. And here I present the detection significance using this plot of the chi-square distribution. And the black histogram represents the empirical distribution derived from the mock simulation that has no parity violation, whereas the orange vertical line indicates the chi-square value measured from the BOSS data. And then the separation between the black histogram and the orange line reflects the detection significance. Basically, the wider they're separated, the higher detection. And in this work, we tested various scales and also binning schemes on the two subsamples for both the CMAS and also for low C. So for the CMAS, the detection significance ranges between 4 sigma and 7 sigma, whereas for the low C, it falls between 2 sigma and 3 sigma. Also around the same time we published our result, another study led by Philcox was also released. They applied a very similar method to the CMAT sample, but made some different choices in galaxy weights and the binning schemes, and also observed non-vanishing detection. With this, let's now move to the discussion about the challenges. So if we come back to the definition of the chi-square, there are basically two components entering this number: the data vector for the 4-point function or the signal, and the covariance that quantifies the uncertainty. So this implies that we need to be mindful of potential contamination, both at the signal level and at the covariance level. First, at the signal level, we can broadly cast them into three categories. There could be instrumental systematics, or observer-related effects, and algorithm-related effects. And for each of these categories, we further tested individual effects. And as an example, well-known systematics in spectroscopic survey is the so-called fiber collision effect. And this arises due to the finite radius of the fibers. Say, if the two galaxies having a very similar angular separation and that are smaller than this fiber radius, and they cannot be both observed in a single exposure, leading to unresolved measurement. And if you want to know more details on the systematic effect, and here you can also check out the link to my presentation from last year. But what we learned from this series of tests is that it's quite unlikely to have a systematic effect that directly coupled to the signal. They are either highly suppressed or they are mostly 2D effects, whereas parity violation requires a 3D mechanism. But now let's move to the covariance level. And this is where things start to become more subtle. So when we published this paper, there were several worries regarding our use of an analytic covariance matrix. And these were very good points, actually, as we made several approximations in constructing the analytic covariance matrix. For instance, we assumed that the underlying field is a Gaussian random field, and we did not incorporate the effect of the higher order multiples of the power spectrum into the covariance structure. And we also ignored the survey geometries. And these approximations, while simplifying the calculation, could potentially impact the accuracy of the covariance matrix. And in fact, we also had a similar concern. Therefore, in our paper, we also presented results using a pure mock-based covariance matrix. So even with this alternative approach, we still see or observed a detection significance between 5 to 6 sigma, and it reassures the robustness of this measurement. However, are we totally happy? Not entirely. For example, we can still ask ourselves, say, if there is a genuine parity violating signal, would we expect to see a coherent oscillatory pattern when observe either the northern or the southern sky? And then to test this, we performed a cross-correlation analysis between the north and the south hemisphere. And if there was a consistent parity violation, we might expect a non-vanishing correlation coefficient. However, in our paper, we find that the cross-correlation between the north and south sky were nearly to be zero. And to address this, we proposed a toy model to explore how it might be possible to detect a statistically significant signal while still finding a very low cross-correlation. And this toy model suggested that we might be working in a relatively low signal-to-noise ratio region. And this year, Korlevsky et al. And took this analysis a step further. They did a very careful analysis by splitting the sky or the data into smaller subpatches. And then depending on how you split and combine the data, they found the detection varies between 0 to 2.5 sigma. And they will be presenting these results at this workshop as well. So one reason for the variability in detection significance could be the fluctuation induced by systematic effects, which arises both from the accuracy of the simulation and from survey systematics. And the marks we use to simulate gravitational dynamics using approximated method, which can introduce biases relative to the n-body simulation. And this concern was highlighted in the work by Fulcox and Areza, where they compared the detection significance using the covariance matrix from n-body simulation and the approximated marks. While they found the significance could vary depending on the choice of simulation, for this study, it is also important to understand the impact of the calibration for the galaxy halo connection for the higher order statistics. And in other words, the n-body simulation are not the ground truth neither. Moreover, due to the computational challenge of constructing the n-body simulations, a common practice is to use a smaller simulation box and then duplicate the volume to cover the entire survey. However, this approach could artificially inflate the error bars and reduce the detection. So beyond the comparison between the n-body and the approximated marks, simulations may not accurately replicate realistic survey systematics, which could also have a non-trivial impact on the significance of our finding. So given all these challenges, there's the question that where should we go from here? So in my view, I would like to push this study in these two following directions. The first is about the robustness of our analysis. So how can we ensure that our findings are reliable to the systematic issues we've been discussed so far? And then beyond the robustness, there's an even deeper question, say, what is the physical interpretation of this measurement? And specifically, can we connect these parity odd measurement to an underlying physical model? And establishing such a connection can allow us to move beyond the statistical detection of a single number, and then also opening a much richer insight into the shape of the potential signals or scales of interest and other relevant characteristics. So next, I would like to discuss future directions from several key perspectives, including developing new algorithms, identifying distinctive features, enhancing the modeling of theoretical frameworks, and also incorporating larger and independent data sets. Let's begin with one of the algorithms, a new estimator that we developed over the past year. Before diving into the details of this estimator, let's first consider an important question. Say, For a scalar or a spin zero field, what are the necessary ingredients for probing parity transformations? So essentially, we need to have four fields. And additionally, we also require to have an operator that connects these four fields. So from the previous examples, we have seen that the scalar triple product plays a crucial role in this context. And specifically, in Fourier space, we need a term of the form like K1 dot K2 cross K3. And the next question is, how can we group or rearrange these four fields? So one option is to take all the four fields as they are and compute their ensemble average directly. Alternatively, we could pair two of the field, apply an operation to each pair separately, and then combine these results. And another approach would be to select one field, apply an operation involving the remaining of the three fields, and then merge the result. And after exploring these different options, we realized that this first approach corresponds to traditional four-point statistics like the trispectrum or the four-point correlation function. While in contrast, the second and the third approach provides this compressed form of the four-point statistics. And the next question becomes, how can we construct an odd observable? So a simple idea is to cross-correlate an odd quantity with an even quantity because odd multiplied by even is an odd. For example, a vector transform as parity odd, whereas a pseudo-vector transform as parity even. And therefore, by cross-correlating an odd vector quantity and an even pseudo-vector quantity, we can obtain an odd observable. So this is the basic idea behind this parity odd power spectrum, or shortened as POP. And this is a work led by Jiamin, and you can find a talk from last year following this link. Moreover, this estimator, shares a lot of similarities to the clustering fossil idea proposed by Donghee Zhong and Mark Kaminkowski in 2012. So just very briefly, in this paper, we constructed two types of POPs. One is a vector POP constructed by cross-correlating a vector and a pseudo-vector as two composite fields. And the other one is a scalar type constructed by cross-correlating a scalar and also a pseudo-scalar, where the scalar field is a single field and the pseudo-scalar is a composite field. And then we tested these POPs using simulations that incorporate a parity violating mechanism following the template outlined in Kuden et al. And for each simulation, we applied two different coupling constants, and one is positive, one is negative. Taking this vector POP as one example in the left panel, the measurement is represented by the dotted curve with arrow bars in red. As a contrast, we also ran simulations using a pure Gaussian random field and applied the same estimator. And in these Gaussian simulations, the measured POPs are consistent with zero, as shown in the gray curves. And finally, we computed the theoretical prediction for the POP in the presence of parity violation, which shows good agreement with the measurement. And this POP has several advantages. First, it is sensitive to different configuration of tetrahedra compared to the galaxy four-point correlation function, where different tetrahedra configuration can rise from different underlying physics. Moreover, they also have reduced dimensionalities, alleviating the typical challenges of computing covariance matrix associated with four-point statistics. And in addition, the POP is constructed in the Fourier space, where systematics often affect configuration space differently compared to the Fourier space. So having the measurements in both spaces can enhance the robustness of our analysis. And moving on, my next point is the distinctive feature. And here I want to emphasize the baryon acoustic oscillations. So the BAOs, they originate from the interaction between radiation pressure from the photon and gravitational collapse in the early universe, where the photons were tightly coupled to electrons and baryons through Compton scattering. As the universe expanded and cooled, the high radiation pressure at the center of each primordial inhomogeneity propagated outwards as a spherical wave, dragging the matter along with it. As the universe continued to evolve, it cooled enough for photons to decouple from matter, and at this point, the photons free stream away and leaving the matter in their position and gets frozen. So this features what we observe today as the BAO pattern in the galaxy distribution. On the right-hand side, we can see the BAO feature measured again from the SDSS using the two-point function by Eisenstein et al. Notice there is a small bump at the scale of about 100 megaparsec over h, which indicates the characteristic BAO scale. And any pattern that existed in the density field prior to decoupling, such as parity violating correlations produced during inflation, would carry the imprint of BAO. And there are like two critical timestamps to consider. One is the end of inflation, and the other is the moment of decoupling. The first timestamp is important because the current model for the parity-odd galaxy 4-point function primarily focus on inflationary mechanism. Whereas the second timestamp, the decoupling, it is the one associated with BAO. And if we do detect these features in the odd functions, they could serve as an independent validation of the parity-odd function itself and providing additional evidence that the signal is true. If we observe a parity odd signal with high enough to noise ratio, but without imprints of BAO, it could also have a significant implication, for example, raising doubt to a prior decoupling origin of the signal. And then to further test whether this idea is feasible or not, we again use the suite of the parity violating simulation with the same model as we use for POP. And here we visualize these simulations. So on the left, this is a slice of the Gaussian random field. And on the right, here I isolate the parity odd component. And here we can see the helical structures in this simulation. And we prepare the simulations using the parity violating initial condition and then evolve them with the matter transfer function with or without the BAO feature. And this setup allows us to directly assess the impact of BAO on the parity odd signal. And here are the odd 4-point function correlation function measured from these simulations. And here we have different channels of the 4-point function coefficients plotted against the index of the tetrahedron configuration. And similar to the previous analysis, we also prepared two sets of the simulations, one with positive coupling and the other one is negative coupling, shown by the blue and also the red curves respectively. In the bottom panel, there are the arrangement of the three radial bands. And we observe several interesting features. We first notice that there's this fishbone shape in these coefficients. And in particular, for some tetrahedral configuration, there is a clear distinction between the positive and negative coupling. And I use these gray vertical lines to guide eyes. As we start with the first configuration, with the free sides to be the closest, the signal-to-noise ratio increases as we increase the third side, but then it drops back as the second side increases by 1 index, while the third side resets its counting. And this alternating pattern just continues until the free sides become comparable in their length, at which point we enter a low signal-to-noise ratio regime where the statistical noise starts to get dominate. And this behavior arises from our choice of the template, which peaks at the soft limit, where one of the wave numbers approaches 0. And consequently, for this analysis, the angular channel of interest of interest are primarily those associated with L3 at the lowest order, namely it equals 1. And here I also show the 4-point function in two-dimensional space by fixing one of the sides and varying the rest of the two. As an example, I take two angular channels for 111 and 221 to demonstrate the BAO imprints on the 4-point function. So the middle and also the right panels are the 4-point function with and without the BAO wiggles. At a first glance, they appear to be very similar, which is expected as the BAO feature only contributes at the percent level in the density field. However, if we take the difference between these two fields as shown on the left panel, we observe a residual pattern on the order of 1%, and this subtle difference highlights the BAO imprint. Finally, we also quantify the detection significance of the BAO feature on the parity odd function. In the left panel, this is the overall detection significance of the odd signal for the positive and the negative coupling constants. We computed the chi-square for both the parity violating simulation and the Gaussian simulations, and then we treated each parity violating simulation as an individual test and then compare it to the width of the chi-square distribution inferred from the Gaussian. On average, we find a 3 to 4 sigma for the overall measurement. In the right panel, it shows the BAO detection significance for the odd 4-point function for both the parity violating and also the Gaussian simulation. We compared the delta chi-square by comparing the cases with and without BAO features. And then we infer the significance similarly by comparing the parity violating simulation to the width of the Gaussian distribution. And for both coupling constant, we found a 3 sigma significance on average. But then compared to a traditional BAO significance quantification, where people usually assume a template for the endpoint function and then subtract the chi-square for the wiggled from the no wiggled one, here we essentially use the data to replace this template. Therefore, we should also interpret the significance in this plot slightly differently, saying instead of just saying there's the BAO significance, I will rephrase it as the significance in rejecting the absence of BAO in the presence of an odd 4-point function. So in case you find anything that is against intuition, and here's why. I also want to note that these results are based on idealized simulations that do not account for nonlinear gravitational evolution or observational effects like redshift space distortion or survey systematics. And additionally, our approach subtracts the BAO wiggles by effectively running the simulation twice, whereas in reality, we have only one universe. But in our paper, we proposed 2 alternative methods for dewiggling in the 4-point function, which I'm very happy to discuss further in the discussion session. And finally, our conclusions are specific to this chosen template, but all these extensions will lead to exciting future efforts. And next, move to the fundamental origin. So here by the fundamental origin, I mean the physical model that describes parity violating signature in the data. They are important not only in gaining insights into physical interpretation, but can also provide guidance in data analysis. And one of the model of particular interest is the axial model. And this is also one of the most well-studied models, and many of the attendees of the workshop are also expert on it. This model is very interesting, as many of you who have studied that it has peaks in the equilateral configuration, where the 4 sides of the galaxy, or depending on the definition of equilateral, are of equal length. Since Matthew will give a talk on this topic during this workshop, I will just briefly outline the basic idea. And the key point here is to consider this additional term in Lagrangian during inflation, where a pseudoscalar, such as an axion, is coupled to the gauge field and also its dual form. If the axion is the inflaton itself, as it slowly rolls down the potential, the motion of the inflaton background leads to gauge field production, and the gauge field then inversely decay back to the fluctuation of the inflaton field. And these fluctuations are then responsible for cosmological observables, such as endpoint function of cosmic microwave background and large-scale structure. So these correlators were previously calculated in this paper. However, in these calculations, and especially for the parity odd functions, involve very high dimensional integrals, and it also makes hard to compare directly with the measurement. And Matthew has made significant progress in simplifying these calculations and reducing the angular dependence down to one-dimensional integrals. And in the future work, we will also extend this calculation for these primordial correlators to incorporate late time and also observational effects. Moving on to the next topic, complementary probes. So if there is a parity violating mechanism, particularly the one that is originating from inflation, as we have previously discussed, it will likely imprint across multiple observables. And these imprints will not only appear in the galaxy data, but also likely detectable in other probes, such as the CMB. However, if we take a closer look at both of the observables, their geometries are fundamentally different, and which is crucial for the parity study. The CMB has a full sky coverage. However, it is also a 2D sphere embedded within a 3D space. And there's also a significant distance between the observer and the last scattering surface. And since the parity transformation is inherently a 3D operation, so probing two small scales on a CMB will make the points appear to lie on a flat 2D surface and thereby losing sensitivity to parity transformation. And then to retain the sensitivity, we need to focus on relatively low angular momenta. But in contrast, the galaxy sample, and particularly the Bose sample, covers only 20% of the total sky, but it allows us to have the access to the full 3D information. And due to the computational and also systematic considerations, we avoid probing scales near the survey boundaries. And also for this reason, the galaxy sample is more sensitive to tetrahedral configuration of equal sides. Although this picture may change in the future, but it holds true at least for the Bose analysis. But then from this point of view, the primary CMB and galaxy distributions are very complementary probes, given their sensitivities on different scales and also different type of models. But that said, there has been no quantitative comparison between these two probes, and that's something I'm currently working on. In addition, there were also two talks from last year by both Focox and also Slepian on this topic on somewhat different angle, and it will be very interesting to check out their talks as well. From the CMB side, we can learn not only about primary anisotropies, but also the secondary effects. As the CMB photons travel from the last scattering surface, they get deflected by gravitational potential of large-scale structure, which is known as the CMB lensing. On the one hand, the CMB lensing gives us access to modes larger than the galaxy sample, but on the other hand, because the lensing kernel has peaks at low redshift, and therefore they also allow us to probe scales smaller compared to the primary CMB. And we are also expecting to hear a talk from Alessandro Greco from this workshop as well. But then as we open up the space, there are various cosmological probes that are sensitive to the parity. And here is a non-exhaustive list. But due to the time limitation, I will not go through each probe. And this is an incomplete list of the reference, as there are also many exciting works that I haven't been able to include. But indeed, I just want to provide a general classification of these probes. And broadly, they can be classified into three categories: the scalar, vector, and also tensor. But then, depending on the parity violating mechanism, they can imprint on one or multiple probes. Therefore, in the future, if we can systematically combine probes across different categories, that would be very exciting. I also want to emphasize that the classification is not unique. Here I made the choice according to the properties of the observables themselves. But alternatively, one can also classify them according to the type of parity violating mechanism. Therefore, there's also a bit of a mixture in this reference list. Finally, I want to move to the data, and in particular, larger and independent data sets. Ongoing and upcoming galaxy surveys, such as DESI and Euclid, are ideal for cross-checking the measurement from BOSS. And in particular, with increasing volume and improved statistical precision, we can relax the requirement in the accuracy of the covariance matrix calculation. And here I use the DESI, the dark energy spectroscopic instrument, as one example. DESI is a ground-based telescope located at Peak in Arizona in the state. It also uses a fiber-fed system to collect spectra. And in this picture, you can see the pedal that holds the robot positioners for the fibers. Currently, DESI is more than 75% complete, and the year one cosmology results are becoming public by the time we have our discussion. And currently, I'm working on the parity analysis for the LRG sample. So the year three has finished its data collection as well, and we can expect the BOSS result to be out very soon. For the year five result, and here is a forecast for the detection significance. In this forecast, we translated a 5 sigma detection for a BOSS-like sample into DESI-like sample, including both emission line galaxy, the ELG, and luminous red galaxies, the LRG. We fixed the total galaxy number counts and varied the number density. By the end of year five, DESI will provide 40 million spectra, and among which we will have 8 million LRGs. Given this large volume probe by DESI, we can expect a much higher detection compared to the BOSS sample. And finally, that brings me to the summary. So in this talk, I discussed about the main challenge in the analysis. And in my opinion, it is dealing with fluctuations induced by systematic effects. And these systematic effects can span a wide range, including survey-related issues, observational effects, and the realism of the simulations. And essentially, they cover factors that are either not well understood or are not properly accounted for in the error bar estimation. And the reason why we are so sensitive to these error bar estimations boils down to this model-independent test. While this approach gives us a lot of flexibility by not being tied to a specific model, it also leaves us somewhat blind when selecting physical scales and tetrahedral configurations. And as a result, we need to analyze a high-dimensional data vector, where even small error bar in each degrees of freedom can accumulate and then lead to a larger overall effect. To address this issue, I then outlined several future possible directions, focusing on algorithms, theory, and data analysis. For example, new statistics, features, axiom models, CMB, DESI. And finally, I want to emphasize that the search for parity violation is really more than a number in the unit of sigma. So even if today we conclude a significant detection, there are still many things to do because we want a complete picture. Whereas if we don't, they still have an important implication for the cosmological model. And finally, I want to thank you for your attention and look forward to our discussion session.